Assalamu alaikum. Hope you are all doing fine. We have learned about the series combination of cells in the previous video. In this video, we'll find out what happens to the current and voltage when electric cells are connected in parallel. Here I have taken three electric cells. I have connected them in parallel. When I say parallel connection, it means all the positive terminals are connected to a common point. Similarly, all the negative terminals are connected to a common point. Here, this free terminal acts as the positive terminal of the battery, and this acts as the negative terminal of the battery. When our cells are combined, it forms a battery. You remember that. Now, I will measure the EMF supplied by this battery with the help of a multimeter. Now, before going ahead, I will set the multimeter to read the EMF. EMF means the potential difference across 2 points of a battery or cell when the circuit is open. I'll place the red probe to this end and black probe to this end. It reads the EMF, which is nothing but 1.68 volt. Now, I will measure the current. To measure the current, I have to connect this in a series with the battery. While measuring the EMF, we connect the multimeter parallel to the battery, this manner. While measuring the current, we connect the multimeter in series. First, I will set the multimeter to read the current. Now, I will include a load. I will connect the anode of this LED to the positive terminal of this battery, and the cathode of this LED is left as such that I am going to connect to the red probe, and I will connect the black probe to the negative terminal of the battery. When I do so, you may observe the LED glow, and the multimeter reads the current. It is around 28.6 microampere. So this battery provides 28.5 microampere current, approximately 28 microampere current. Now I will measure the voltage, that is the EMF and the current supplied by individual cells. First I will measure the voltage supplied by individual cell. For that I will desolder this these electric cells with the help of soldering iron. Now touch it here. Now I check the voltage or the EMF with the help of multimeter. First I'll check the EMF of this cell. It is 1.68. For second one, I'll remove the insulation. Now it is also 1.68 volt. Now I'll go for the third one. This is again 1.68 volt. This shows that all of them provide the same EMF. When they are connected in parallel, they provide the same EMF. So there is no change in the EMF when they are connected in parallel combination. Now we'll measure the current supplied by these cells individually. For that, I will connect this LED in series with them. Before that, I'll set this to read the current. The LED glows and multimeter reads 28 microampere of current which is flowing through this LED. I'll check the current supplied by this cell. It also read 28 microampere. Now I will check the current supplied by the last cell. It also provides current more or less similar to other cells. Here the current supplied by this one is 29.6 microampere. This shows that when electric cells are taken in parallel combination, they provide the same voltage and the current is also same. To discuss the parallel combination of cells, I have considered n number of electric cells connected in parallel. When I say parallel combination, it means I have connected the positive terminals of all the cells to a common point A. Similarly, I have connected the negative terminals of all the cells to a common point B. Here point A acts as the positive terminal of the battery and the B acts as the negative terminal of the battery obtained by the combination of these cells. Here Xi, this letter is Xi. It represents EMF of the cell. Here I have considered that all these electric cells have same EMF represented by letter Xi and the internal resistance is R, common for all these cells. The point A and B is connected to an external resistance capital R. When I measure the voltage across R, it is found to be V. And what is this EMF? EMF is the voltage across a cell or battery when they are not connected to any external device. Or in simple word, voltage across a cell or battery when it is in open circuit. Remember that. Now I'll find out the total EMF and total resistance of this circuit to find the current. First, total EMF. Now I have told you in the previous video, the voltage or EMF remains the same in case of parallel circuit. So here the total EMF will be nothing but Z. It remains. Now total internal resistance. internal resistance of this battery can be obtained easily with the help of the method we followed in case of parallel combination of resistors. There we studied that the total resistance of resistors connected in parallel is equal to the reciprocal of effective resistance. Here RE is effective resistance or total resistance offered by the circuit, a total internal resistance. It will be equal to the sum of reciprocal of individual internal resistance, 1 by R plus 1 by R plus 1 by R. Like we have n number of cells, so plus up to n. The nth cell will also have R as the internal resistance. So beside this I write n to represent that it is nth cell. Now I'll rewrite the same here for better visibility. 1 upon RE. We go to 1 upon R, 1 upon R plus 1 upon R up to nth term. Now when I add all these things, you may find that the denominator is same. So we need to add the denominator. This kind of terms can be added by taking LCM. Here the denominator have common term, so R is taken as such. Then I need to add all these things. Whatever present in the numerator, we need to add. No? There will be n number of terms. So I take it as n in numerator. So 1 upon RE is nothing but n by R. To find the RE, effective resistance, I need to take reciprocal of this. When I make any changes to left hand side, the same thing I do to the term present on right hand side. So RE, 1 by RE is n upon R. RE equals to R upon N. This is the effective resistance offered by the battery or total internal resistance of the battery. Now I have obtained the expression for RE, which is nothing but the total internal resistance offered by this battery. Now in the place of this battery, which is made by connecting electric cells in parallel, if I take a battery of this kind, which said to have internal resistance RE, and I connect this to the same resistance R, capital R. Then they are in series. This is the circuit we get. This circuit is the equivalent circuit of what is shown here. Now the total resistance of this circuit can be obtained by adding capital R with the total internal resistance. So total resistance of the circuit is equal to the sum of RE plus capital R. I take this one as the equation number 1. Now, I take this one as equation number 1 and this as equation number 2. Now using equation 1 and 2, with the help of Ohm's law, I am going to get the value of I. What is Ohm's law? Ohm's law is equals to IR. From this, I value is obtained in this manner. Here V is voltage and R is resistance and I is current. So current due to this battery, current due to the battery will be obtained by dividing total EMF with the total resistance. What is the current? Here I take the current as I. I is the current. Produced by the battery. The total EMF is Xi upon total resistance Re upon capital R. This is the expression which gives the current supplied by the battery built using electric cells connected in parallel. Now we will discuss two special cases. Now before going ahead, I will rewrite the final expression that I have obtained for electric current. Right here, I is equal to Xi upon Re plus capital R. Here Re is R upon N. I am going to write the value of Re here for the simplification. Xi for Rn plus capital R. Now see, for simplification I am going to multiply this term with N. Actually I am using this method to remove N from the denominator present in this term. Then divided by, when I make any changes to the numerator, the same thing I have to do with denominator as well. So I will multiply this term with N as well. R upon N plus capital R. Okay. N Xi upon R N upon N plus NR. Now this N and this N will cancel. They divide each other. And what you obtain is N Xi upon R plus N capital R. This is the another expression for I. I take this as equation number 1. This gives me current supplied by the battery. Now I will discuss the special case. Now first take a case 1. In case 1 I consider R, that is internal resistance of the cells, to be very large compared to external resistance. When R is very small compared to capital R, in equation 1, we neglect NR. What is the reason for neglection of NR? The reason is NR is a very small value. When we add this with a large value, it doesn't make any big difference. So it we can neglect this. Then equation 1 becomes something like this: n xi upon a small r. Here n, this equation can be written as n into xi upon small r. Now I take this one as I1, so the equation will become something like this: NI1. The current supplied by the battery is equal to n times the current supplied by each cell. Here I1 is the current supplied by individual cell. So this shows that when the internal resistance is very large compared to external resistance, the current supplied by the battery will be equal to n times the current supplied by individual cell. Now I'll take a case 2. In a case 2, I consider cells having internal resistance very small compared to external resistance. If it is so, then in equation number 1, R is neglected. Small r is neglected. Now, equation 1 becomes something like this: n xi upon n r. Here n and n here cancel. We get a new expression which is equal to I xi upon capital R. This shows that the current obtained by a battery by connecting cells with least internal resistance will have current supplied given by this equation. This shows that the current supplied by a battery built using cells connected in parallel will have advantage when the external resistance is small compared to internal resistance offered by electric cells. I hope this video is useful. If you have any kind of doubt related to the topic, kindly put a question in the comment section. Thanks for watching.